the Carbon Leadership Forum. Oh, thanks for joining us. So this is going to be a session on timber and wood products. And thank you very much for joining us today, the Carbon Leadership Forum, the Toronto chapter. We have with us today, okay, got it. Let me go to the next. We're going to be talking about wood. I'm going to go to the next slide. First, we're just going to have an acknowledgement of, since we are a Toronto-based group, just like to acknowledge that the land that we're on is traditionally the territory of many nations, including the Mississaugas of the Credit, Anishinaabe, and the Chippewa, and Haudenosaunee, and the Wendat people, and it's now home to many diverse First Nations, Inuit, and Métis people. We acknowledge that Toronto is covered by Treaty 13 with the Mississaugas of the Credit. Just some ground rules. If you could please put your questions in the chat, because we'll have a question period at the very end. And if you could figure out how to use the speaker mode, that might be the best way to look at it. Please mute your cameras, and also if you could turn off your audio. And just to let you know that the session is being recorded, and that will be available after the session for your review and review. Great. So let's get, without much further ado, let's get started. So we have two speakers with us today. We have Peter, who will be starting the talk, and Peter is from the Canadian Wood Council. It's a think tank basically to help designers, people with promoting wood in Canada. Peter, I can't see my bios, so unfortunately that's what I'm going to give you as your bio. But Peter's here to help, and we're going to introduce Nicholas after with his presentation from Element 5. So Peter, if you want to go ahead and share your screen, please.
As soon as you share yours off.
Share mine off. Thank you.
Okay. Everyone see that okay? And can hear me okay? So thanks very much. It's a pleasure to be here. I'm based near Vancouver. The Canadian Wood Council is a technical support organization, as Susan mentioned. We work with architects, engineers, contractors, developers, regulators, fire officials, building officials. We don't sell anything. We don't sell any particular wood product, but we try to provide technical support on how wood products can be used appropriately. One of the things that over the last several years we've been looking at is there's tremendous amount of opportunity for wood use as codes change and as focuses on carbon change. And so these are some of the things that we regularly present on and work on. For the purposes of this session, I'm really just going to focus on these ones here. So the carbon aspect, some energy use and high performance, design for deconstruction. There are labor issues, there are construction opportunities, there's technology and stuff, but for this, because it's the Carbon Leadership Forum, I'm just going to focus on that as to talk about this. The picture on the right, by the way, is a proposed building in British Columbia. It's a hybrid building, so it's got concrete, it's got steel, it's got wood. And it's designed to be a passive house. So it has a wood curtain wall, wood platforms, but there's, as I say, wood, steel, and concrete in it. And I think that's the way it's going to go. Is for larger buildings is using materials where they make sense and where you get that you can achieve your aspirations. So. The wood industry has traditional products like lumber that have been around for generations. They're often used in single-family homes. I think more than 90% of all the single-family homes in Canada are built with these traditional products of lumber, plywood, OSB. However, some of these products have been advanced so that the codes have changed to allow them to be used in other buildings. And I'm thinking things like mid-rise construction, where you can have light wood frame up to 6 stories across the country in the National Building Code. The National Building Code, and we'll get into this a bit later, is changing to allow encapsulated mass timber construction using products, but these traditional products that we have, the light frame structures, can be used in buildings up to 6 stories and can be used for tall wall systems. They can be used in, offices, schools, that sort of thing. But there are some new products. CLT is one of those. I'll get into what the mass timber products are, but the CLT is one of them. And they can be used in traditional buildings like this office building, which happens to be the building I'm in right now, is a 2-story office building, similar to a lot of those medical buildings and small service buildings, mercantile on the bottom, offices above. And then there's some new products. This particular one shown there is wood fiber insulation. And these new products can be used, as I say, in traditional buildings, as well as new construction and new technologies. This is the Origine building in Quebec City, and this is the building completed. And it's an all mass timber structure. So there are opportunities for these different products, as we will see. So typically, the heavy timber or the mass timber has been raw lumber, not using glue. These are the hammer beam design in a cathedral, several hundred years old in Europe. But the pictures on either side are from buildings that are old, but heavy timber and mass timber. The one on the right, for those of you who ever get out to Vancouver, there's a pub called the Gastown Steamworks in the Landing. It's a 9-story building that is actually closer to 11 stories in height, but it was made with heavy timber, solid Douglas fir columns, and that nail laminated timber deck. So this is, it's sort of, we've been resurrecting the fact that we forgot that we knew how to build tall wood buildings using heavy and mass timber. So I just showed you some nail laminated timber. I'm just going to go through these quickly. The nail laminated timber is simply dimension lumber that is nailed together with nails that go through 2.5 of the members, so that they provide support in one direction. So that if it's a span or if it's a single directional cantilever, this is a very cost-effective way to do it. It's simple. Oftentimes it can be built on site. Other times it's manufactured off-site, delivered. Glue laminated timber, I'm pretty sure everyone's familiar with that. It is using chemical means to fasten the members. It's a very efficient use of wood. And when you consider that these glue lamps here would probably be 3 or 4 lamella thicker if it was in dimension, if it was a solid wood beam. And that's because these little defects here, these knots and stuff, are offset by wood on either side of that particular lamella. So from an environmental perspective, you're getting greater efficiency of smaller trees. You're able to use smaller members and build that up into a heavy timber structural product that is consistent in strength and consistent in cost and dimension, and it's a much more stable product. So dimensional glue lamp timbers have been used for 70, 80 years. Laminated veneer lumber, this one is using the same veneers as are used for plywood. It's a peeled process. The veneers are a little bit about 1/8 of an inch thick, and then the resin is a phenol resorcinol resin that does not off-gas. A general rule of thumb for off-gassing, if you're concerned about that, is if it's a structural veneer used, it must be waterproof, and it must be structural from the minute it leaves the plant. So these products the glue is inert, does not off-gas, there's no chemical changes. That's just a rule of thumb. Laminated veneer lumber is produced in it's not an extruded product per se, but it's made in a continuous sheet, can be purchased in lengths up to 64 feet long, which is the length of some of the maximum length on some of the trucks, but it's typically sold in narrower bits and is used for headers. It can be used for columns and beams. It's a very efficient use, again, of wood, which reduces the overall impact because you get higher utility. Laminated strand lumber, it uses thin wafers, if you will. It looks sort of like OS-oriented strand board, but the resins are coated, the wood is coated in a resin and then pressed. So this piece that you see down here might have been 9 or 10 inches of loose pack, and then it's pressed to produce a strong, stable mass timber product. Parallel strand lumber is a product that was invented in Canada. It's about 30 years old. It uses a strip of 1/8 inch thick veneer. Most of that is second growth Douglas fir, at least in British Columbia. And the panels or the product it produces are extruded bolts, if you will. They're about 14 inches by 18 inches. They can be glued together to be built up. It's not typically used as a panel. It is used as a column or a beam, and it's the strongest engineered wood product we currently have in the world. It's about 6 times as strong, but rated at about 3 times as strong as a solid lumber component. A couple of others that are new to the market: dowel laminated timber. Instead of using nails, which are would hamper post-installation modification, or glue, which requires curing time, it uses wood dowels. So the holes are, the wood is laid up just like a nail laminated timber, pressed, and then holes are drilled, and dowels that are about a little bit bigger than the hole are pressed in place, and it locks the timber in place. The nice thing is, because these dowels are just every few centimeters, you can machine doors and window openings without worrying about hitting nails. And another product that is not made in Canada but is available in Canada are mass plywood panels, where they use 3/4 inch or 1 inch plywood. They build those sheets up to create a very strong and very durable mass plywood product. And the one that seems to be garnering a lot of attention these days, cross-laminated timber. I'm going to leave that to Corey. Corey, you can explain that process. I'm not going to get into that because we've got an expert on the presentation. So, what are some of the considerations around forests and carbon and wood? Well, I'll take you through these, and then we'll discuss them as I go through. First of all, there's forests. We have logging operations. There's concern around harvest levels, and there's also what happens on the land base after the harvest. Are emissions, do emissions increase? Does the land get replenished? These are all concerns that people have, and for the most part, once you do the research, you realize that there are impacts, but these are being addressed. For example, logging is in Canada, most of the wood is owned by Canadians. So these are some of the issues around forests. There's also embodied carbon. What goes into making the products that we use? How much energy, how much carbon? This is all being addressed through life cycle analysis, and it's something that you as carbon leaders recognize is an important part of our considerations, that we can't just ignore what goes into the building. We have to focus on that as well as the operational performance. Biogenic and stored carbon. This is a bit of a wild card in that wood is a biogenic material. It comes from nature, and it's going to go back to nature. The certainty of that is we know that it's going to go back, but we don't know when. So if it went back to nature the day after we used it, it would have 0 carbon benefit. If it goes back in 500 years, that's deemed basically to be permanent carbon. So, and we would get 100% credit. So we'll talk a little bit about that. If you've got any questions, perhaps I can answer it. And then there's the end of life. Again, we don't know what the time frame is on that. We don't know what the scenarios are. Personally, I like to say, if you're going to calculate end of life, calculate it on the worst case scenario for today, because presumably materials are going to be more valuable in the future, and we'll have a better sense of what to do with those materials. So if you focus on the worst case and do your analysis, then perhaps you're going to be better off down the road by being able to find alternates to what we today would consider a worst case. So I'm pretty sure most of you have seen something like this, the carbon cycle, humans, nature, whether it's wildfires, disease, decay, landslides, hurricanes. They affect what happens on land and puts carbon back into the atmosphere, and then forests and land and ocean take it back out. So the concern that most of us are facing is not part of the cycle that we had, and we're adding carbon into the atmosphere. How do we address that? So again, for those of you who are doing LCA, you're familiar with the A1 to A4 elements of life cycle and analysis, looking at inputs, looking at outputs, looking at residues or waste. Where do they go? How do they get used? And what's the impact? The wood sector that I deal with is looking at the extraction and transport and manufacturing of products. That's the embodied impact. We don't get involved so much on transport to site. That's going to vary with location. It's going to vary with product. It's usually by truck or rail. We also don't necessarily get involved in the construction process, but we work with architects and engineers to create some efficiencies and value engineering of products and use of those products. So there's a carbon impact to value engineering. If we don't have to use stuff that is either high carbon or as much of a material. And I'll give you an example, and Nick, no disrespect, if someone is looking at the impact of building a light frame home or a CLT home, the CLT home will sequester more carbon, but has a higher embodied impact. So we have to balance what is the ultimate impact that we want to achieve or want to reduce, and pick our materials accordingly. And this is within material silos like wood, and also across material silos like stone and masonry, wood, steel, and concrete. So the wood industry doesn't get involved in demolishing buildings per se, although there are some codes and standards we've been working on for designing for deconstruction. We'll get into that later. And then at the end of the day, what happens to that product when we no longer have a use for it? We've fully recycled, we've recovered, we've reused, and it ends up going to the landfill. So we have to address those. Those are the areas in the red rectangles that we deal with. One of the programs that I'm overseeing for the wood industry is the National Research Council Low Carbon Assets Life Cycle Analysis project. And what we're doing is gathering information from all the sawmills, plywood plants, OSB plants, mass timber producers, to provide the National Research Council with a life cycle inventory database. It's very comprehensive, it's very complex, it's going to take some time. We hope to have it all done by the end of March. NRC, or National Research Council, has provided support to the concrete industry as well, and then they approached us. We'd like to get this information from the wood sector. So we'll be gathering this embodied impact information, the first parts of that, so that designers and procurement people within government are going to be using this to add to their decision-making process. So this is a procurement strategy by the federal government that is likely to be used by the provincial and municipal governments as well. So that's this extracting raw materials, transport, and making products. That's what the LCA squared is, and we hope to have that data. It will be available to any designer. So if you're a designer, an architect, engineer, or a contractor, and you want to say, I want to find out the material choices between, say, a truss or an I-joist or a built-up mass timber, you'll be able to calculate those embodied impacts. So forests, it all starts with forests, and you've probably heard of sink, sequester, and substitute. It actually starts with sustainable forestry. And I think that's really important because in Canada, most of our forests are owned by Canadians. 93% is owned by us, not by companies. In fact, we also have a very high level of certification. Canada's certification is about the equivalent of the next 8 countries or 7 countries combined. So the vast majority of our forests, and our forests account for about 400 million hectares in the country. 300 million could produce wood, and about half of that is certified. 164 million hectares are certified under one of 3 different systems. Another thing that's going on is the National Research Council and Canadian Forest Service are looking at forest management and how that can be used to mitigate climate change, which is basically pulling carbon out. So they looked at a whole bunch of different methodologies. They looked at bioenergy. If we convert to bioenergy, what does that do? We looked at longer lived wood products. We looked at harvesting less or better utilization. I talked about taking small trees and making glulam. And what they found is that there's no silver bullet. there's silver buckshot. So we have to do a little bit of everything if we want to optimize the carbon benefit from our forests. So there are people who say we have to use wood for everything. There's others who say let's just convert fossil fuels. Others say let's just lock up our forests and do something else. When you look in balance at what is best from carbon, it's a mix. It's conservation, it's utilization, it's better management, and it's also using wood in longer lived buildings. When we look at the forest carbon, typically a forest will achieve a stasis where in some of the very old forests, they're losing as much carbon as they are absorbing it. That's so you get to a net zero. It's a carbon stasis, and over time that remains static. There are some big trees that hold a lot of carbon, but a lot of trees that stored carbon have also died. So there you get the stasis. When you take some of that and you lock it up into longer lived buildings and structures, you're actually able to store that. So you're getting a little incremental benefit. But also, if you use it then to substitute where you can for other products, then you get the displacement of those emissions. Now, I want to say there's no perfect material. Steel rusts, concrete spalls, wood burns. But what we as users and designers have to do is understand how do we integrate these products to better reflect what we want to achieve in cost, in function, in beauty, in performance, and embodied impact. Time is a very important factor when you're considering carbon. If you look at this chart, this is showing the radiative forcing of a CO2 emission. The largest radiative forcing is in the first 50 years post, not post, emission. So that means that if we can delay those emissions to a time perhaps when we're better able to adapt or find ways to mitigate, we have to understand that. So when you emit is important. In fact, if you avoid a ton of carbon today, you don't have to avoid for over 4 tons of carbon in 80 years. That's the cumulative benefit of an avoided emission. So there's justification for including the sequestered carbon in a building. And the longer that building retains its carbon, the greater the benefit over time. But as I said, if you build a building and it gets destroyed the next day, all of your embodied impacts have still occurred. Likewise, since materials do go back to the atmosphere, it's not a 100% permanent storage. So the carbon benefit of sequestered carbon is somewhere between 0 and 100%. That may seem glib, but that's what we have to figure out. At the end of the day, though, the IPCC has recommended that we need to use our forests, use wood from sustainable forests and use them in longer lived products. And that will generate the largest sustained mitigation benefit. And this was validated again in 2013 and 2019. I show this tool because so much of this picture is an LCA study out of Australia. So much of our effort goes into operational performance. And yet the codes really only affect about a quarter of the emissions associated with the building. In this particular case, fully a third of the impact over the life of the building was embodied. 23% was the operational performance and the embodied carbon from operations. So it makes sense to focus on embodied as well as performance. When it comes to extending the life of carbon in buildings, we need to design for deconstruction. We can't just get tired of a building and knock it down and try to salvage what we knock down. So there are some codes and standards that we have been working on at CWC for disassembly and adaptability, for deconstruction. We need to shift our thinking to designing for the future and future reuse, not just the first time single use. And there's a lot of benefits to that. There are carbon benefits, there are cost benefits, there's landfill benefits. We've got local economy because it's always going to be deconstructed by local people. So I think if we can start to pay attention to designing buildings so that they can be deconstructed, then we're going to be better able to fulfill some of our aspirations around circular economy as well. The circular economy just the material itself. The other thing we need to do is we need to design and build buildings that will last. And one of the best ways to do that is to make a building that people love. Wood is often criticized, oh, it rots, it burns, it's not very strong. Well, that's our fault. If we design something so that it will fail, it will fail. We need to understand that materials don't fail people, people fail materials. And if we design a building that is adaptable, flexible, enduring, can be maintained, is resilient, and can withstand the environment in which it is built, we're having a long-term carbon impact. And I think that's a shift. We can't let our egos or our economies drive just the carbon decisions. I'm often asked why we would build with wood. And I think, well, gee, we've got a product that's a carbon sink. They're renewable, recyclable, reusable, organic. The forests clean the air and provide habitat, recreation, oxygen. It's all of these good features. So the question I would ask is not why wood, but perhaps if not wood, what? If we're going to build, can we increase the amount of wood we use to fulfill what we want for that building? It doesn't mean that you're building a building only of wood. And there's a picture in Chris's presentation, or sorry, Nick's presentation, that has an igloo. That's the only building I can think of in Canada that's built with a single material. All the rest use more than one. So with that, I will stop sharing so you don't have to look at my screen.
Great. Thanks a lot, Peter. So next we're going to have Nicholas Zeeb from Element 5. Hi, Nick. You can start sharing your screen, please. So Nicholas, he's a registered professional engineer with a structural engineering background from Western and an honors business degree from the Ivy School of Business. So at Element 5, Nick is the manufacturing engineering manager, where he's developing methods for driving down the costs of mass timber products. And he combines his experience in structural engineering, construction project management, and cost estimation with a passion for climate action. Thanks, Nick. Go ahead.
Awesome. Thank you very much for the introduction, Susan. All right. Hi, everybody. My name is Nicholas Zeeb. I'm, as Susan mentioned, our manufacturing engineering manager here at Element 5. So Element 5 is a leader in CLT and glulam production here in Ontario, and I'm excited to be representing our company for this presentation with the Carbon Leadership Forum. On the slide here is an image of our brand new fully automated CLT and glulam production line in St. Thomas, Ontario. And this is the beast that we're hoping will help drive the mass timber industry skyward in Eastern Canada and the United States. So diving into our agenda, there's a couple topics that we'll be talking about, specifically an introduction to mass timber and to Element 5 as a company. We're going to be touching on the state of mass timber as an industry in Canada. And then we're going to move in how to design mass timber with carbon in mind, specifically from the perspective of a manufacturer. So as an intro to mass timber allows us the opportunity to use natural, renewable, and sustainable building materials in construction. We know that forests grow to store carbon from the atmosphere, but that carbon storage stalls as the forest gets older, as Peter mentioned in this presentation. By harvesting forests before this plateau and using a proactive planting strategy to replace the trees that are cut down, we can effectively replace these forests as we continue to build with wood. The benefit of this process is that the carbon footprint of mass timber is often much lower than a concrete or steel alternative. Finally, it should be noted that the carbon from the trees are stored in the building for the life of the structure, again, something that Peter discussed in depth in his presentation. However, it's important to consider the strategy then of what we're going to do with that wood after the building life cycle has been completed, so we can keep those carbon emissions out of the atmosphere as long as possible. We have an image here of Element 5 state-of-the-art facility in St. Thomas, Ontario. It's a big box building that's about 137,000 square feet with an annual production capacity of 45,000 cubic meters of CLT and 5,000 cubic meters of glulam. We're PRG 320 certified, and we were in full production starting April 1st. The image on the right there was the first panel that came off our line in December of 2020, and they've been rolling off the line like hotcakes ever since. Our wood is sourced from Ontario forests, and that wood is FSC certified. So I'm going to do a quick rundown of the elements that we produce. I already mentioned that we make CLT. The CLT panels that we produce, the maximum size we can make is 16 meters by 3.5 meters. That's some of the largest mass timber panels that can be produced in North America. And we also produce the species grade spruce pine fir, at a V2 or an E1 grade. We also produce glulam, and glulam we have a max length of beam that we can produce at 16 meters. The width and depth that we can produce are as required for the project, and the species that we manufacture is SPF, 20FE, and 20FEX. So now I'm going to dive into a little bit about the scale of production specifically for element 5. So I mentioned some numbers earlier that I think require some additional context. If we take our annual production capacity of 45,000 cubic meters of CLT and 5,000 cubic meters of glulam, that adds up to 50,000 cubic meters of mass timber production out of our St. Thomas facility annually. Now, when I first heard that number, it was hard to understand what that meant in terms of actual construction. So that is roughly equivalent to 22 Brock Commons buildings produced annually. Of course, this got me very excited the first time I heard it. That's a lot of mass timber that can be built. And I really saw the potential for what Element 5 could do for the mass timber industry in Ontario. But before we get too excited, I want to zoom out a little bit and really consider what 22 Brock Commons buildings really sounds like at the end of the day. I'm assuming a lot of people on this call, we're doing this for the CLF Toronto chapter. I'm assuming that most of you are in Toronto, but I'm sure everyone is well aware of the immense construction going on across Canada. So, quick Google search got some images of various construction projects going across Canada, Toronto, Vancouver, Calgary. And as can be clearly seen, we're really pushing forward with urban development, with concrete and steel clearly being the material of choice. The only major city I could find committing to sustainable construction was Winnipeg, continuing to harvest building materials from the frozen tundra. It's important to realize, though, that even Winnipeg will not be able to follow through with sustainable construction once climate change kicks in and starts to impact their ice reserves. All kidding aside, mass timber production in Canada, of course, is growing. If we look at this map from NRCan, there's clearly lots of growth in the industry, with most of the competition existing in glulam and CLT. And it's exciting to see that there's so many manufacturers across Canada. But again, I do want to take a step back and really understand what this scale means compared to our competition of steel and concrete. So if you haven't got a chance to look at, NRCan's interactive portal for mass timber construction, I highly recommend it. It's great to see where mass timber projects are going up across the country, where the opportunity and growth lies, and where the manufacturing capacity is. But however, I want to focus on that one number in the middle of the portal there, 702 projects. This is the number of mass timber projects that have been built in Canada since 2007. That's the start of the portal's timeline. Again, this sounds like a great number. However, if we look at the value of building permits across the country in May of 2022 alone, there are billions of dollars of construction happening across the country. 700 new projects, while a great amount of growth for the mass timber industry, is ultimately a drop in the bucket. Now, if we can take this even just one step further and look at the scale of production globally, if we look at by 2025, it's anticipated that the global production capacity for CLT is somewhere between 2.5 and 2.8 million meters cubed of CLT. If we compare that to concrete, though, it's expected by 2025 we'll have 25 billion meters cubes of concrete annual production capacity. I know we can't necessarily say that 1 meter cube of concrete can be replaced by 1 meter cube of CLT, but it is important to note here that that's a 4 magnitude of difference, which is quite a large way to go to make up to be a truly competitive building material. And so if we consider the adoption of mass timber across Canada and effectively mass timber adoption across the world as an S curve, we are very much likely still at or before the inflection point of major growth and adoption. Now, I bring all these points up not necessarily to bring doom and gloom and be nihilistic to these carbon discussions. In fact, I think that having this perspective is incredibly important to make sure that we focus the industry and help mass timber grow in the best way possible for what it's effectively able to be used for. So therefore, given that perspective, I want to point out some things that we need to consider. While mass timber is a great solution to lower the embodied carbon in a structure, we simply cannot put all our eggs in that basket. Other solutions need to be explored, particularly for building typologies where mass timber is not practical, or there's heavy code limitations like for buildings over 12 to 18 stories. The other point I want to make is that investment in mass timber buildings and mass timber production needs to happen across the value chain, still in droves, both from governments, owners, private developers, designers, engineers. All of us are required to keep accelerating the pace of mass timber industry so it can truly become more than a drop in the bucket. And the last point I want to point out is that designers and engineers, in order to further push mass timber as an industry, need to clearly understand its limitations to ensure that the structure is designed efficiently to bring down both cost and also to bring down embodied carbon to encourage faster production. Okay, so that brings us into the last segment of the presentation, designing with carbon in mind. And so where should we focus? There's a couple points that I want to bring up, specifically that the volume of wood in the final structure can be considered to be directly proportional to the embodied carbon and the cost of the building. And we're going to go through these points one by one in future slides. The next point is that hybrid solutions should be considered wherever possible, where mass timber as a sole solution does not make practical sense. Peter did note that we typically don't discuss location in terms of the embodied carbon, but I'm going to. I think location is an important thing that we need to focus when considering the output of carbon when building, specifically with mass timber. And then the last point we're going to discuss is the first principles of mass timber manufacturing and how that impacts construction. So starting in that first point, where wood volume can be considered directly proportional to embodied carbon and cost, this is an example of the different layups that I pulled directly from Element 5 specifications. And I want to focus on the simple fact that CLT is generally comprised of a discrete number of odd layers, specifically 3, 5, 7, and 9 layers. I point this out because for that reason, CLT is unlike concrete, where it's not unheard of that if you are at your capacity limitation, you can just add additional rebar or increase your slab thickness by 10 millimeters to achieve those capacity requirements. With CLT, if you design a building that goes over the capacity limits of that panel thickness, you then have to consider potentially adding 2 additional layers of wood to meet your capacity requirements. Let's go through an example of this with Element 5's span tables, which are provided on our website. So let's say we're in the first category of this table, designing a residential building with a 1.9 kPa live load. In this case, we're typically trying to make a 5-ply 175 panel work, which is our most cost-effective and relatively simple to design to. In this case, the panel is governed by vibration at just over 6.1 meters. If, unfortunately, the panel clear span goes beyond that span limitation, then we have to start considering design alternatives. The first thing that we're going to do is we're going to consider, can we go from a V2 grade panel, which is what this table is based on, to go to an E1 grade panel. That's the next strongest grade up. But if even going to the next grade doesn't get us the capacity that we're looking for, we then have to consider going to a 7-ply panel. We would typically recommend going to our thicker lamella counterpart for ease of manufacturing, which is the 245 panel. So if all of that happened, then that means we started from a 5-ply 175 panel and increased it to a 7-ply 245, which represents a 40% volume increase, which is directly going to impact the cost of the structure as well as the embodied carbon for the structure. The next point I want to discuss is the lateral system of a building. Here's an image from our YW affordable housing project in Kitchener-Waterloo. We're going to get into this project in more detail later on in the presentation. The lateral system of this building was built entirely out of CLT panels, using the demising walls and some of the hallway walls as lateral elements. This type of solution is really great for low-rise buildings, removing all structural concrete above the foundations. However, we found, as we've been experimenting with this typology in a sense of scale, we found that this solution really works well up until about 6 stories. And this is a bit of a rule of thumb. It can be explored over that, but just a point of, if you're above 6 stories, we might want to consider looking at other options. Once we go above 6 stories, the number of walls required for the lateral system increase the costs of the building, increase the embodied carbon because there's more volume of wood, and it makes the architectural layouts more difficult because we have so many walls to deal with. We recommend that above 6 stories to consider an alternative material for the lateral design, which can directly bring us into hybrid solutions. So again, any replacement of steel or concrete to mass timber will help with the embodied carbon of the building, assuming it's designed efficiently for mass timber. This is a study done by Thornton Tomasetti that showed that most of the buildings that they were designing, the majority of their embodied carbon was found in their floor structure. So if a full mass timber solution isn't practical, finding a way to replace only the slabs with CLT floors can still have a major impact on the building's embodied carbon. So I'll give a couple examples of hybrid solutions that we might be familiar with here. The building we all know and love in Canada, Brock Commons, used concrete cores for its lateral system, while the framing and the floors were mass timber. T3 Sterling, that is going up in Toronto right now, is using steel braced frames for the building perimeter to resolve its lateral forces. And then finally, 6 Oarsman Road in London, UK. I know this is outside of Canada, but it was a great example. It's a great example of where steel framing made the most sense for the project, yet we were still able to replace the floors with mass timber, helping the embodied carbon of that project. Moving on to location. I do think it is important, considering where the mass timber industry is, specifically for CLT, glulam, NLT, where it is as an industry in its infancy. Location does matter when considering embodied carbon. So if we look here, Element 5's facility in St. Thomas is about a 2-hour drive outside of Toronto. Now, we're of course not the only player in Canada. So if you're looking for other mass timber providers, I've got here the snippet from the NRCan map that I mentioned earlier. So you can see with those brown wood colored dots throughout the map that there are other mass timber suppliers, but they are located all over the country. So so at that point, shipping mass timber potentially across the country is going to have a larger carbon footprint than ordering mass timber from a manufacturer that is closer to the construction site. So it's important to consider that, because unlike concrete, where there might be a ready-mix plant around the corner, that simply is not the case with mass timber industry at its current stage. And lastly, I'm going to touch into the first principles of CLT production. So again, I'm going to show that image of that CLT panel coming out of our X-Press in the factory. And there's a very basic and important point I want to make about CLT production. CLT is manufactured as a rectangle. We are very good at making rectangles as shapes go. It's my favorite shape. Now, a surprising amount of my job is actually figuring out how to fit rectangles into shapes that are not rectangles. And the embodied carbon of a structure can increase because of that waste from those offcuts to make those shapes fit. So let me jump into a couple of examples here. On the left here, what is a wall panel that we produced for one of our projects, where the windows of that wall were CNC'd out. This is a great solution for construction. You just have one giant wall panel that you lift in place and put on site. The problem is that we did have to manufacture that full CLT panel to make that wall in the first place. So unless those rectangles that are cut out are used in the building in some other way, the embodied carbon and the cost of that wood that is being cut out is effectively lost, but is being accounted for in the project. Now, if I look at the image on the right, this one is not our project, and I'm not even going to comment on the crazy CNC work that's there in that wall, but I do want to point out that Tetris-shaped floor panel that's being erected. Again, a rectangular panel had to be manufactured to make that panel. So that negative space that's no longer there is now being, is contributing to both the cost of the building, the embodied carbon of the building, but it's not having a positive impact on the actual floor area. So again, something to consider with construction. I'm going to drive that last point home with a very simple example, and I apologize for how rudimentary it is, but if we consider this plan view of a potential building shape, we have a box. As you can expect, we're very good at putting rectangles inside rectangles. So this might be a floor panel layout that we might propose, assuming that the structure is sufficient below. But now let's consider a second building shape where we have a potential angle here. And again, not to say that we can't necessarily build in this building way, but it's something to consider is that when we're making our panels, we have to actually manufacture those panels on the right there to have enough length to make it to the end of the building. But when we do that, we're effectively losing all the areas marked in red. Now, effectively, what I'm proposing here is you could have a floor that is sawtooth like that, and it would have a similar embodied carbon for that floor plate. But because we have that diagonal, unless, again, those triangles that are lost can be used for something else, the embodied carbon of the building is going up, The cost of the building is going up, but it's not contributing to the floor area. So with all that in mind, I'm going to show, we took all of those principles that we discussed earlier and we applied them to a project that we built last year, the YW Affordable Housing Solution in Kitchener, Ontario. This was a project that achieved great success, such that our mass timber solution won out as an affordable housing solution over a core slab structural alternative. Here's an image of the building under construction, almost fully assembled. So we use CLT for the floor and the roof slabs, for the demising walls between the units, the elevator shafts, the stairwells, and the exterior wall panels. The panels you see on the outside of the building are approximately 10 feet wide and 4 stories tall. And we installed those exterior wall panels in only 2 working days. Showing a time lapse of the construction here, we got on site day 1 on September 23rd. By 8 working days later, we were on the 2nd floor of the building. And by 20 working days later, the building was fully assembled. So again, this solution utilized the principles that we described earlier, be it that we considered the manufacturing first principles CLT to reduce waste. We had a location that was incredibly close to the facility, and all the other principles that we described to be able to bring down the cost of this building such that we were able to be cost competitive while also being sustainable and environmentally friendly. For those interested, here's some perspectives on the inside of the building. On photos on the left are one of the apartment units, and the photos on the right are of the lobby of the building and of the hallways. Now, before I end my presentation, I do want to point out, I think the one point that I want to make sure I avoid is that while I'm suggesting to consider building these buildings with CLT first principles in mind, that doesn't necessarily mean you can't be creative when building with mass timber. Again, showing there that tiny image on the left there, that is our YW model that we built last year in Kitchener. We also built a 2-story version of the same building in North York for another affordable housing project. And we've now been experimenting with a lot of different versions of the same typology, showing that you can get fairly creative with the building typology as long as you're, again, considering the limitations of CLT, how it's manufactured, and putting all that together to make sure that the building is designed as effectively as possible. And so that is my presentation today. Thank you very much for listening. I've got my contact information here, but if you're looking for a potential project opportunity or sales discussion within Canada, I've also got Lee Scott's contact information here as well. Thanks very much for listening, and I look forward to the questions.
Great. Well, thank you very much, Nick. And also thank you, Peter, for that. I was checking the chat, seeing there was some conversation going on. And I also noticed that Peter was very active, writing quite the responses to some of the questions. Thanks, Peter, for that. Yeah, so that was very helpful. I saw also, I was talking separately with some people in the chat. Some are just curious about learning a bit more about embodied carbon. So I thought, well, you definitely have come to the right place. The Carbon Leadership Forum has definitely a lot of that going on. So I did see, let me start at the beginning. We had a question at the very beginning with Ben. I'm not sure if Peter, you got that one. Yes, you did. You answered it a bit, but maybe just a little bit more. If you want to mention, you were using the term that owned by us, that the forests are owned by us, but not companies. And you just wanted to clarify. And I saw you did go into some detail.
Yeah, the private land, I think Canada has about 7% of the land is held privately. That's in our houses, our cities and stuff like that. The rest is under Crown ownership. You know, it's different in different provinces. In the Maritimes, about 60% of the forest is owned by private individuals, farmers, landowners, etc. In British Columbia, it's 93% is owned by the province of British Columbia. So it varies. Canada is large. Most of our natural resources are on Crown land, and that's what I mean by we as Canadians own it, not a private entity.
Perfect.
And it's different in the States. Much of their resource extraction is done on private land.
We had another question from SWS Oman. Is there any lifespan difference between mass timber buildings and the concrete structure? Just wondering if any lifespan difference between mass timber building and concrete structure. So,
you know that. Sorry, Nicholas. one of the things that we forget is buildings typically, it doesn't matter the material, wood, steel, concrete, stone, masonry, for the most part, buildings don't get torn down or because the material runs out of the utility. It doesn't get broken down because the building materials fail. It's typically a land change, a cost evaluation change, a function change. The owner gets tired of it. They want something bigger or better. And that's where most of the buildings are. There's, I think, one of the oldest concrete buildings, the Pantheon. That's 2,000 plus years old. We've got buildings that are 500, 700, 900, 1,300 years old in wood. I think all of those were designed by having people understand what the material has to face. And if we don't take care of a building, if we don't take care of a steel bridge or a wood building, the material will fail us. But that's because we fail it. I really believe that we can design buildings for longer, and I think we have to.
Peter, Nicholas, did you want to respond to that as well?
Yeah, I can touch on that, and I completely agree with Peter's point. As an anecdotal piece of evidence as well, Element 5's Toronto office is in the Toronto Carpet Factory, which is an older mass timber structure that has large sawn members for its beams and columns, but then an NLT floor system. And it was built in the early 1900s. Like I think it's over 100 years old now. So as an example of a building that we have in Toronto that is mass timber and is still around. So I think that is an important point to make as well.
Thank you. I see we have someone with a hand up. So Ken Caruso of Cement, if you want to, there we go. Thanks, Ken.
Hey, thank you. Good presentations. Thank you very much for both Peter and Nicholas. I put my question there in the chat, but I just thought I'd ask directly. Peter, you mentioned it. Hybrid buildings, and each material obviously has its strengths, its weaknesses. There's no perfect material. I think you said steel rust, concrete spalls, and whatnot. But can you talk maybe a bit more about end of life? And just as I see in the chat there, I'm here in Vancouver, and on sort of a personal note, I'm continually appalled at how destructive we are in these are stick frame buildings, and obviously it's a crazy housing market still in Vancouver, and we basically generally still tear down these buildings, and off it goes to landfill. Again, you probably know the cement industry has been working to try to get some of that materials, construction waste. But again, the challenges, and this is not, I think, a challenge to CLT specifically, but maybe talk about what some of the things you're doing or pushing on, again, end of life and recycling.
Well, Ken, I couldn't agree with you more that destroying and then salvaging, that seems to be the extent of our willingness to do material recovery. And I think it's wrong. I think, we've got all this material, and, whether it's precast concrete, those slabs can be pulled and reused somewhere. Do they? I don't know. So we have this human desire that I want something new. I want it for me. And we make really bad decisions that we don't need to make. We say, well, deconstruction is more costly. Yes, it is. Designing it, I compromise design. I can't sort of bolt it together because it's not going to look the way I want it. Well, that's ego. I hate to say it, but we let ego and money drive a lot of our decisions. The one thing that I think mass timber buildings do have over some of the other materials, it's typically mechanically fastened. So it could be deconstructed. But let me tell you, no one's going to take a CLT wall and turn it back into lumber. So we have to capture the function. That's what circular economy is capturing the function or the service. And whether it's a building is designed using concrete precast panels, all of those panels were made somewhere else. They could be pulled off and used somewhere else. But that's an ethos that we as designers, builders, and owners and material suppliers have to work to find solutions on. And I guess Ken, a lot of the CLT buildings, they have a concrete topping. How do we design it so that we can resalvage, so we can salvage that wood or that floor system? And I think I would really like to see more collaboration and less competition. And I've chatted with Adam Auer, who's the new president. And I think he would like that as well. There's, as I said, there's only the Igloo is, and I stole your thunder, Nicholas. Only the Igloo is the only building made with one material. All the rest, we got to integrate these folks. So we have to be smart and we have to understand how we can integrate them.
I agree, Peter. I think
so,
we need that collaboration. And like I said, my question is not specific to CLF. I think your examples are very good with with tilt-up concrete as well. We know that those materials are recycled ultimately into aggregate, but the panels could very well be physically reused. It doesn't happen. Maybe just the one point as well on hybrid buildings. Nicholas, you had the pictures of Brock Commons. Our son's at UBC. He's actually been living at Brock Commons for the last 3 years.
Lucky guy.
I've got some great pictures, both out of the building and inside the building. It is quite impressive, and it is. I think you mentioned off the top, Peter, a hybrid structure. I think you've done the math. It's about 62% by weight of concrete and concrete toppings and elevator shafts and all that good stuff. It was, I'll say, quite impressive to see it go up, and being assembled. So maybe a bit more impressive than the Kingston structure, but just because obviously it's 18 stories. So anyway, I think for us, yes, Adam Auer has really emphasized that we want to collaborate, we want to work, because I think we need all of those building materials. So thank you.
Well, if you're in Vancouver, I'm on the Sunshine Coast, so let's grab a coffee one day.
Well, this is very impressive here for this Carbon Leadership Forum Toronto chapter to have so many people from the West Coast joining in. So this is very exciting. And I'm looking at the time, and I just want to thank both Nicholas and Peter for your presentations. There's going to be a recording available for everybody. And thank you very much, Ken, for that question. It really is about collaboration. We have a climate emergency here, and we have to work together quickly to come up with solutions. So for the next Carbon Leadership Toronto chapter event, stay tuned. I know we're working on having a social event where we might be taking a break for the next month. Everybody's on holiday, but please stay tuned, and thank you everybody for joining. Take care. Bye-bye.
Thanks, Susan.
Thank you.